Hello everybody and welcome to tutorial 12. Today we're going to talk about electromagnetic radiation. Before we're going to jump into the subject, I want you to see a video. I'm going to press this red button and then you should see the video.
Holy shit!
Look at the ball.
What? What do you see?
Do I look better looking?
God, you look weird.
Let me see.
They look nice on you.
Wow. It's weird. I don't know how to explain it.
What do you see?
The houses, like I can tell what color they are. Like that one right there.
Yeah,
That one right there's brown.
Yeah.
That one's red.
Yeah, you're right.
I did not know these were different colors before I put them on.
What about this nice purple bush?
This is a funny. I'm not sure I know what this color is. Is that orange?
Yeah, it's like a mustard.
Somebody painted that house orange?
It's like a mustard. Here, come here. Let's walk over here.
Purple's beautiful.
Yeah.
I've never seen purple before.
Really, not even like a shade of it?
No. That's purple, right?
Uh-huh.
Stop sign, Fred. Stop sign.
What? Where's my car? What the frick? That's what?
Glad to have you back. So what you saw today in the video, it was that we actually grasp the reality to our eyes. Our eyes are sensitive to energy. This energy is called light, okay? We are seeing light. Like in the previous tutorial, we talked about that our ear sensitive to another waves, which are the waves of the air, the vibration of the air molecules. So right now we actually sensitive to another wave, which is the light, the electromagnetic radiation. And we actually are limited in this area, the visible light. In the video you saw some people that have some issues with seeing all the colors. So this is all the colors we can see. And in the past there was a researcher, Frederick William, and he decided to test the different colors of light. And what he did, he put here, measure the temperature here of the purple one. Let's do it in the same line. He measured the temperature of each color. Okay, here the temperature here, the temperature of the blue light, the temperature of the green light, the temperature of the orange light, temperature of the red light, and he said, you know what? I'm gonna also put here another thing to measure the temperature, just to understand what's going on in the room and compare the colors. So we see the purple and we see a low temperature, and then you look to the blue, you see it's getting higher, and then to the green you say, oh, it's getting hotter. To the orange, it's getting hotter. To the red, it's super hot. And then what's going on after the red? You saw that it's even hotter here, but here there was no light. And then humankind understand that they cannot see everything. There's other stuff that they can't see, which is the non-visible light. So if we're gonna spread all the light that we have, so this is the visible light, what you and I can see, what our eyes can sense. But if we're going to go above the violet, the purple color, we're gonna get to ultraviolet, above the violet color. And this is actually the reason when you go to the beach, you put sunglasses, right? To stay safe, okay? And another example is if you go even higher in the frequency, the intensity, the energy is even higher. But think about that. If I have an eye, okay, this is me looking at something. So this is a low frequency, right? And this is a really high frequency, right? A really high frequency. So what's happening in a second, you get these, all the peaks, the maximum and the minimum, right? In a really small, tiny fraction of time. That's what's gonna go here. That's what's gonna come inside here, right? So this is really intense. We go to X-ray. With the X-ray we can observe bones. We can go through the body. So this is really dangerous. And beyond that we get to radioactivity, which is super dangerous. Okay, change the atom. Okay, this is really powerful. And we can go the other direction, right? To take the frequency to be lower, and then we get to remote control and infrared. If I use the air condition that I have here in my room, here I have, you see here, this one, I actually sending light that you don't, this is a flashlight, you don't see it, but right now I operate the air condition using these waves that we cannot see. And if I'm gonna go even more, cellular phone, Wi-Fi. Actually right now this room is so colorful with so many frequencies and waves you cannot observe and see. This is the Wi-Fi that you have in your house. And if I go even more, I get to radio waves. When you drive your car, right? And you have these radio waves, right? So this is what's happening in the sky. All the places are with radio. Right now I can open radio if I have one and hear the radio because the waves are all over the place. So we actually inside the full of radio, of electromagnetic radiation without noticing it. And also when we do notice it, but a really small fraction. So I want you to think about the color blind people and think about, wait a minute, I'm actually also blind. I cannot see everything. And there's other animals that can use this, for example, the infrared, for example, snakes, right? When they want to hunt, they use the infrared vision to see stuff. Okay, so we actually, all the humans are kind of have some color blindness, okay? Let's do a simple question for the beginning, okay? So we're gonna do a simple question and then we're gonna dive to the really electromagnetic radiation, the really super thing. So I'm gonna remove all this beautiful drawing. Perfect. This is good. And the question is gonna be, let's start with the easiest one, which is me driving the car. So there's a radio station. I'm here. Let's do. This is the car, okay? And I'm driving, having fun in my car, right? And I have an antenna on the car, right? Which observe waves. So, and here nearby, not that near, let's say 80 kilometers away, there's some radio station using 107 FM. Okay, this is the radio station and it's also sending some, what? EMR, electromagnetic radiation toward me in the car. And my question to you is, when I open the radio, I press on, right? Inside my car, on to the radio, give it a voltage, I want to hear it, okay? How much time it's gonna take me to actually hear the sound of the radio? I want to hear the radio, not white noise. I want to hear the radio. So you for sure remember that if I move in a constant velocity, x equal to vt. The distance equal to the velocity multiplied by the speed. So if we talk about EMR, the first thing I want you to understand that light, okay, moving the speed of light, and not only the light that you can see, also the light that you cannot see, which means radio wave actually moving in the speed of light. Okay, how much time it's gonna take me? It's gonna take me some t, which I don't know, And the distance from the antenna, sure it's something like that, but if we're talking about long distances, these two lines can actually be really the similar thing. So I can say that this is 80 kilometers. So this is 80 multiplied by 10 to the third. C, it's a known constant, which is 3 times 10 to the 8, right? Really fast, okay? Sure, in the air, the velocity is a little bit reduced, okay? But in general, it's a good approximation also inside air. So let's go with that one. So I can get T outside of the equation, which is 80 multiplied by 10 let's do it 10 to the 4th, right? Delete is 0. Here 3 multiplied by 10 to the 8. So in general we have 10 to the minus 4. Sorry, this is 10 to the 8. This is 10 to the 6. Sorry about that. No, 10 to the 8. Okay, I'm 8. I think it's 6. Never mind. This is not the issue. But the result is actually is what? The result is 0.000123 another 0. That's it. 27 seconds. This is so fast. Okay, you cannot blink in this time. It's super fast. Okay, so that's what I want you to know. Speed of light. This is the idea from this easy question. Let's continue with the easy question. So my second question to you is how the wave look like. Okay, this is the wave. It's coming toward me. How it look like, or how I like to say, what is the wavelength? Okay, of this wave. So let's delete this one. We know this one. We know this one. So what is the wavelength? So we know the equation of waves. Remember for the previous tutorial? So the equation of wave is actually the velocity equal to the frequency multiplied by the wavelength. Right? So the wavelength is actually V divided by the frequency. So V, we know it, right? We know V. V is actually the speed of light. We just talked about it. And what is F? It's given. The radio station tells you on which frequency to choose. But I want you to notice that a radio wave actually going in the megahertz. Okay, mega. Mega is 10 to the 6. Okay, so if you in the language of radio, it's sure that you're talking about mega, right? That's like you and me in life. What is your height? So you say your height. So you know, if you're from the US, it's feet. If you're here, it's meters, right? So it depends where you are. But if we're talking about if you are in the realm of radio station, you're talking about megahertz. So this frequency is actually 107 10 to the 6 hertz. Okay, that's the idea. So we got everything. Let's put it inside the equation. So the wavelength is actually equal to C divided by 107 6, and this is equal to what? To a huge wavelength, 2.8 meters. Okay, what does it mean? It means that you take the wave. Okay, so if this is the wave gonna have, it's gonna look like this, but this distance from here to here, this is the wavelength, right? It's gonna be almost 3 meters, okay? It's gonna be so wide, so long, okay? And this is the reason it's actually keeping energy. So using these frequencies, these frequencies, you're actually keeping the energy. You're gonna learn about it in physics 3. I don't want to talk about it too much, but remember in the paragraph, in the graph that we did with the beautiful pictures, I actually drew the frequency going to that direction. Remember the energy getting higher. And think about it, that lambda is a constant divided by F. So the relation is gonna be the opposite way. So if I want to talk about lambda going to the other direction, they are inverse to each other, inversely proportional to each other, right? So this is a low energy. Think about 10 to the 6. Wow, this is like, you know, this is a really big. No. Frequencies can go really crazy. Okay, so actually when you go in this direction, you understand it using less energy. So this is a really low energy dissipation of the wave. let's not going into it. We have another stuff that's super important. Okay, the last thing I want to ask you is what is the wave number? The wave number. So for now, I just want you to remember that the relation between the wave number, which is k, and we're going to talk about the wave number in the next question, but k is the it's the opposite thing. It's like, okay, let's talk about it in another form. K is equal to 2 pi over lambda. So I just want you to now remember the formula, okay? So this was 3, right? Almost 3, 2.8. So, okay, this was 2.8, this is almost 6, so you can calculate it, okay? But I want you to have this formula, and we're gonna talk in the next exercise really deeply about this idea, okay? But right now I want to keep it simple because we're gonna see it next. So let's go to the real hardcore EMR question that I talked about. We finished the warm-up, okay? So done with the warm-up, let's move on. So, my uncle, really cute uncle, and he fall on his hand. He loved to do skateboarding and stuff like that, and he fall on his hand, and I already knew, like I was a skater in the past, so if you're falling in that way, you probably broke your hand. So I took him with the car and we went to the hospital to check him with the X-ray, exactly, EMR, okay? So let's draw the idea, okay? So let's start all over again. So X-ray emits, okay? Emits EMR. That's what I want you to know. And what is actually EMR? It's electric-magnetic radiation. Let's talk about the electric. So I have electric field, okay, which is a vector, and this change in space and time, okay? Remember that we have the pool, and remember that the waves are changing in time and place, right? The spring change in place and time, right? So this this electric field is a distribution in the world that's moving in space and time, and how it moves. Okay, so we have an amplitude, so this is the magnitude. Let's have more space. So this is the magnitude of the electric field. This is the magnitude, and it's actually changing. It's changing like a sine wave. So this is a sine. And inside the sine, oh, there's a lot of interesting stuff inside. And this is a vector that's changing in the y direction. Okay, soon everything's gonna be clear, promise you. So there's a change in space, kx. Remember this k? Yes, this is it. This is it. And there's changing in time, minus omega t plus phi. Okay, so this is let's draw what's going on in the sea. So this is my uncle. The sunglasses, oh yeah, a cool hat, and smile. Yeah, I don't care, I broke my hands, but I'm super cool about it. So this is probably his broken hand, okay? And he's standing, and he said, sorry about that, kind of thing. And he had his skateboard with him. So, and then we have, let's do it in red. Then we have the X-ray. Of course, X-ray don't have a color. We cannot observe the color of X-ray. It's above violet. I have a violet shirt. It's above the violet, right? The UV, the ultraviolet. It's above the violet, and it's above also the ultraviolet. So it's getting to the place you cannot see. Okay? So that's what's going on here. But let's do it red. Okay? So if I drew here an axis, so I'm gonna say that this is the Z direction. Okay, and this is the y direction, so this is the z direction. So, sorry, this is the x direction. So the wave is actually moving in the x direction. K is about the movement, where I'm going to. So it's actually going to this place, but it's changing in y. What does it mean? It means that the sinus is actually changing in the y direction, okay? Changing in the y direction. So it's changing in y, but going through X, and then it's hit the hand, okay? Hit also thermally, but also hit like punch it, okay? That's I want you to think about it. So it's coming through, this is the X-ray machine, the X-ray gun, okay? And there's two things that are given in the question. Is the first thing is at location 0, at time 0, the electric field is actually equal to 0, okay? It starts from nothing, okay, and then it's pop up, okay? But my question to you is, what is the direction to the electric field? Is it pointing at the y direction, or is it pointing at the minus y direction, right? So it's that you can understand from the derivative. Where I'm change, derivative is change. So where do I change? So they say, dude, it's changing in a negative, in a positive way, okay? Positive way. If I'm going to the y or the minus y, we still don't know. We're gonna figure this out, okay? But I'm increasing. That's what happened to me. I'm increasing, okay? Nice. Changing in a positive way. Okay, great. So the first question is, what is the phase? The phase of this term is the first question that we have. What is the phase? Okay, so what is the idea of the phase? So think about it. I have sinus, okay, which means I'm nothing, and then I appear. This is sinus. And what is cosinus? Cosinus is actually I'm the best, I'm the highest point, and then I'm shrinking and disappear. This is the idea of cosinus and sinus, okay? And phi is actually, if I'm not cosinus or sinus, I'm something in the middle, I don't want to be this or this, okay? So phi is actually come to fix this idea. Because we know that not everybody start with the maximum, and not everybody start from to be down there. Somebody start in the middle. So this is the idea of phi, to change the sinus, or sometimes to say that the sinus is a cosinus if you want. Phi can do it, okay? But phi is to be more general. So let's find phi. So the first thing that we can do is, actually we can put this and this, right? We can say that E at time 0, at location 0, equal to E0 sinus of 0, because the x is 0, at time 0, and then I have this phi. And this is equal to what? To 0. That's what they told me. So I can get rid of this, and I can say that sinus is actually equal phi equal to 0. So which phis are actually capable of taking this sinus and kill him? Okay, let's do sinus. So this is the sinus. Start from nothing, get the best, and then repeat himself all over again. That's what's going on. So who can make this one 0? So I can look at here. Oh, this one can do it. This is location pi. Oh, this one can do it. This is the location 2 pi. Oh, this can do it. This is 3 pi. This is, okay, this is 4 pi. Okay, so I have a lot of suspects. There's a lot of guys that can kill sinus, okay? A lot of murderers, a lot of killers. So I can actually say that phi actually equal to n multiplied by pi. Okay, this is all. I don't know who gonna kill this sinus, but there's a lot of options of doing that. Okay, I can see that all. N can be positive and also can be negative, whatever, okay? This is important. So we actually use this one, and we find a lot of suspect to be phi. Now, what we can do? Correct. We can try this one out. This one out. What's going on here? So let's clean this one. Let's clean also this one. And we are actually staying with this. And let's ask. Okay. Okay, got it. So what is the derivative of E? By what? By time. If you see dot, it's usually about derivative by time. So if I want E dot, it's actually equal to E0 sinus becoming a cosinus, right? This kx minus omega t plus phi stay, but I have internal derivative, right? So the internal derivative is taking outside some omega t, and this one must be bigger than 0. Okay, so I can cancel this one out, and if I want to cancel this one out, right, I need to flip the side because this is a minus, right? So I actually get that I'm smaller than 0 cosines, and let's not forget to kill this and this because we're talking about location 0 and time 0. So we're actually staying with phi. Okay, perfect. And we know that phi is kind of this kind of person. Okay, somebody love to do this, some love to do this. I know that phi is love to do this. Is whole multiplication of pi. And what is cosines? Let's do cosines. Okay, so cosines start from nothing, and then it appear. Okay, so let's draw that one. So this is, sorry, I confused. Cosine start from the best and then it's falling down. So this is cosine. Sorry about that. Okay, perfect. So this is cosines, and we know that we can look only at these places at multiplication of pi, right? So multiplication of pi is actually this one. This is here to here it's 2 pi. I repeat myself, but in the middle, boom, you are pi. Okay, that's a place. Sorry, I'm looking for places that are negative. Places that are negative are actually these places, right? These places. But I can see that I can use this. I need to choose a negative places. So if I'm thinking about it, thinking about 2 pi, I could not choose 2 pi because a 2 pi with the cosinus is exactly positive. So n must be odd, not even, odd. So of course it's repeat itself. It's not matter if you add 2 pi or 4 pi or 6 pi. It's repeat itself with the 2 pi, so we can choose one in the sequence. So we're gonna choose phi equal pi. Okay, so right now you can write this term here as pi, and if you write this one as pi, it means that you use this given condition about the wave. Perfect. Okay, so we found this, and now I want you to draw yourself the electric field, but I want you to notice something. Okay, so at the beginning, remember, it's 0, so you must draw it from this point. The beginning, it doesn't have any value at y, but then in changing in y and go to what? To the minus, right? Why? Because sinus pi, it's negative. These two cancelling out. So let's go to the negative. So you go to the negative direction, and this is the electric field. At this point, at that point, at that point, this is t equals 0. And this is here, here, and continue on, okay? I want you to understand that this wave, this electric wave, is actually captured inside xy domain, okay? Xy plane, okay? Nothing is popping out. That's what's going on. It's changing, it's moving at x, but it's changing at y, sometimes positive, negative. And this wave is coming through the hands, okay? It's gonna change. This is gonna increase, and this sinus function gonna change. Okay, it's gonna move, gonna come to the hand. Okay, that's what I want you to think about. Okay, perfect. So that's happening in the draw. Keep this drawing. Okay, we're gonna add stuff to it. Perfect. So my question to you, okay, in which direction it's moving? So we talked about that. Which direction the wave is moving and which direction the wave is changing. So it's changing at y. This is where it change. Electricity change in value. Okay, magnitude. Okay, magnitude. And in which direction it moves? Okay, it moves at x direction, and the direction you are moving actually called k. No, it's not that. This is the direction you are moving, you call it k. Okay, and this is where the magnitude of E is changing at y. Okay, really important. And now I want to ask you something. Remember how I called this radiation? I called it electromagnetic radiation. Exactly. So there's actually also a magnetic field, and for that reason this subject coming along, and this is the reason we need to learn about waves in physics too, this class, because in this part of the class you cannot separate them. Electric and magnetic fields combined creates light. Okay, so we're talking about light today. So what direction of the magnetic field? So I'm gonna give you a trick. Okay, you see this thing, this axis? So no matter the orientation, I want you to remember, okay, this thing, let's do it in a really crooked way. Okay, never mind this crooked, let's do it in this direction. Okay, this direction and this direction. Okay, so this is 90 degrees, this is also 90 degrees, this is also 90 degrees. This is the axis. So the axis is always like this. There's the K, which this is the direction where the wave propagates, okay? And there's the electric field, which is 90 degrees, the direction of the electric field, okay? This is E direction, this is changing value, okay, sorry. E, the direction of the electric field, okay? And there's also B, a magnetic field. And they're all what? Perpendicular to each other. Okay, that's what I want you to remember. In that way, okay? That's what's going on. They're always perpendicular to each other. So if X took the K, the direction, the propagation of the wave, if it took it, this is its place, and E took the Y, so the only direction that left out for the magnetic field is Z. Okay, that's what I wanted to remember. Z, okay, or if somebody captures something, the other one gonna get it. And we're gonna do a little bit more complicated thing in the next question. But from now on, I want you to remember that they're all perpendicular to each other. That's what's important for this section. Perfect. And the next question I want to ask you is, what is the amplitude of the magnetic field? If this is the electric field, what is the amplitude of the magnetic field? Okay, so for that, it's another concept that I want you to remember. Okay, the concept is that the electrical magnitude, okay, of the electric field equal to the magnetic one, but there's some constant in between of them. And the way to remember what is this constant, okay, is to understand the units, okay? This is volt per meters, okay? This is the unit of electric field. Remember what is for magnetic field? It's Tesla. This is the unit, Tesla. And Tesla, it's a gigantic units, okay? What do I mean I say gigantic units? If I say, you know, let's give you a magnet of 5 Tesla. Like, I think 5 Tesla is the biggest magnet I found in the world. Like, not human-made magnets, but something you can find in nature. I don't think it's exceeding this value. And electric field, you can find many stuff really high, really huge. Thunders and stuff like that, okay? A huge electric field. So this number is usually really tiny, really small, because they have its magnificent units, okay? So you need to put here a huge number to compensate and help this guy, because he got this huge unit, so this one need to be small. And this constant is constant you're pretty familiar with. It's the speed of light. How bizarre this is, okay? So there's a relation between the value of the electric field and the value of the magnetic field. And this relation is through a constant that we discover way before we understand waves. This is the speed of light, okay? So that's what I want to remember. And now you got almost everything you need to find B. What is B vector? B, X, T. So we know the constant. We know that the amplitude is gonna be a E 0 divided by C. This is B0, we found it. And of course, if this is a wave, it's also a wave, so let's do a sinus something. Okay, I don't know what. And we also talked about the direction. We said it must be at the Z direction. Why? Because they're perpendicular to each other, and if this one and this one perpendicular, these are perpendicular to each other, so there's only one solution that is perpendicular to both of them, which is left out to be the Z direction. And the second thing I want to tell you about light, that in light, the electric and the magnetic field are synchronized, which means they appear the same. When someone is big, the second one is big. When somebody disappears and getting smaller, the other one getting smaller. Okay, that's what I wanted to remember. So I do these two lines, which mean it's the same thing that's going on here. So it's moving in the x direction, it's changing in time, okay? And you have this phase that says, I'm not a sinus, I'm not a cosine, I'm something in between. Okay, this is, you have the same thing inside. So let's draw it, okay? So let's do it in purple, okay? So it's gonna go to the negative, right? First line, the electric field, it's gonna go to the negative. And when this one reaches to 0, this one reaches to 0, because they have the same thing here, right? And then it's gonna go up, right? Plus Z, this go to the plus Y, this go to the plus Z. And then again. So this is, and they're perpendicular to each other, right? It's like, let's use something, okay, here it is. So they're perpendicular to each other. One is at the Z direction, and it's changing like this and coming toward you. And one is at this direction, it's coming toward you, right? That's it. Here it is, like this, okay? Okay, so it's changing in this direction. So when one is at maximum, right? So both of them at the maximum, okay? And then they change to minimum, maximum, like it's I don't have the coordinate to do it. Okay, if it helps you, okay, let's just try it. Okay, so this one is going like this and this one is going like this, so it's like this kind of thing that coming toward you. Okay, so this, I'm moving at the K, and this is what's happening if I move in the minus K. Okay, away from you. Okay, if this was helpful, leave a comment below. Okay, so let's continue. So the magnetic field, it's looking like this. The errors of the magnetic field in each point is pointing only at the Z direction. Okay, only at the Z direction. Sometime positive, sometime negative. Okay, so that's what's going on. You can think about the magnetic field as a lock inside this wall. Okay, the Z and X wall. And you can think about the electric radiation actually looking, the electric field looking at the floor, at the XY direction. But that's what's coming on to the hand. Okay? And this one can go through the skin of you and me. But boom, it's hit the bone. It cannot go through the bone. It's coming back. Okay, that's what's going on. That's how we can see the bones. Okay, the bones are so dense it cannot go through them. You need more energy to go through them. Okay? So this is the idea. Perfect. Okay, so another concept that I want to say, okay, so if I'm going through that one, what I'm actually doing, okay, if I'm going to hit you, spoof, you're going to feel the energy. Let's talk a little bit about energy, okay? So, what is the energy that go to the hand, okay? So let's talk about a new concept, okay? Let's go new concept about the hand. I'm leaving this one because this is important. So the new concept is actually what is the pointing vector. Pointing vector. And what is the pointing vector? If you want to understand what is something in physics, you're gonna say, wait a minute, tell me the units. I want to know the units. If you know the units, you know what it is. Okay? So what is the unit of the pointing vector? We sign it with S, it's a vector, and the unit are watt per meter square. Okay? And what is watt? Funny. What is watt? What is actually joule per second. Okay, I didn't necessarily talking about energy, right? How many do you earn? 300, 400, 3,000. Doesn't say anything. In what time you earn this? Bill Gates earns $17 in each second. Now you're talking, if you make $17 per day, maybe it's not a good, you think, it depends where you live, right? But it's not the same, okay? So this is what, okay? It's power, actually, it's a unit of power, okay? And what is meter square? Meter square is actually meter and a meter. So this is area, okay? So this is a kind of improvement to the idea of power, okay? Of watt. It's actually watt, the joule per second per area. So this idea is actually joule per second per area, meter square. So this is the unit of the Poynting vector. Now I understand. It's if I have an area, okay, think about a solar panel. If I have a solar panel, I want to observe some light, okay, to get energy. So I get some joules, okay, but how much? In 1 hour? In 1 hour I get 100 joules, okay. But if I'm increasing the size, right, of my solar panel, I'm gonna get more energy. So this is the kind of thinking here, okay? But think about solar panels, okay? So I want to ask you, what is the Poynting vector, okay? The Poynting vector of this hand. How much energy, okay? You can think about it. Okay, let's give it the area A. What's the name that I give it? Yeah, let's call it A. Let's call it, this is one is A, okay? The area. So that's the idea here, S, okay? So I clean this one up, and now let's calculate it. So what S actually equal to? It's equal to E, the electric field, cross B. These two vectors. But don't forget to divide by mu 0. That's all. Okay? And in our case, E and B are always perpendicular to each other. Okay? They're always 90 degrees angle. Okay? So if we're going to use this idea, we can say that S is actually E magnitude multiplied by B magnitude, okay? And in which direction the cross gonna give me, because the perpendicular, it's gonna go at the K direction, which makes sense. If the distribution coming in the K direction, where the energy is going to? Yes, the K direction, perfect. Okay, so let's put this one, let's put this one. So here I have E0, and I also have this sinus, right, inside of it. To change the magnitude, right? Let's do here these two lines, which means what was before. So the magnitude of the wave is changing, the magnitude, and B is actually E0 divided by C, and also this sinus, the same thing, right? And divided by mu 0. So actually the total thing is S equal to what? To E0 square C mu 0 sinus square with the same thing inside. So we found what is in direction of K. Okay, so we found S. Okay, found S. But remember what were the unit of S? S is actually a more complicated thing. It's the unit is it's joule per area meter square per second. Okay, this is the idea, right? So if I want to know how hot the hands could be, how much energy actually being transferred here, okay, the joules. So what I need to call, it's called actually the intensity. Let's do I for intensity. And the unit of intensity is a joule. Okay, intensity joule. So what I need to do to determine actually to get this joule, first of all I need to get rid of the area. So if I know the area of the hand, let's say A, so this one is actually equal to A multiplied by, let's do S, okay? I give here space, okay? For a reason. But I did not finish yet. What else determines? So if you, for example, you go out to the sun and you want to get a 10. If you do it for 1 hour or you do it for 3 hours, right? So how much energy did I gain? How much time did you spend in the crazy sound that's going right now in Israel Beach? Huh? Okay, in Tel Aviv. So you need actually also to take into account the time, okay? So for the reason that it's actually repeating itself, right? Because every time that I finish, it starts the same all over again. So let's say if you want to know what is the time, if you've been exposed to, let's say, a period time, okay, t. You start from some point, changing, and then coming back to the same point you originally started. So this is usually what you do. Let's calculate it on. So right now we need to do average. Okay, let's do the average of a time period. And before we're gonna do it, okay, I want to explain something. Okay, and if I want to take average of you, the class, okay, all the students that I have here, okay. So what I'm gonna do? I'm gonna do this thing. I'm gonna say that the average height is to sum all the heights of each student. How much students that we have? Let's say that we have n, capital N students, right? This is the I student, and we start from I equal to 1. And we count the first student, what's your height? 10. Sorry, 10 it's not reliable. 1 point something, 2 meters, 1 point something, and going on and on and on. I sum them all, and then I divide it by the number of all of you, right? This is how I do average. So let's do an average using time. And the funny thing is that time, okay, it's not something, it's not quantum time. Time it's like continuous, okay? So between 1 second to 2 seconds, there's infinite values, okay? So many values, okay? So we need to generalize this term to be more specific. So the first thing I'm gonna do, okay, so let's put this S, okay, here. So the first thing I'm gonna do, I'm gonna take the value S, okay, as a function of time, of course. But I'm gonna sum all the times that I had, okay? So let's divide the time to dt. Okay, so this is the time, this is called capital T, this is the period time, so we're going to divide it to small, this is dt times, and I'm going to sum them all. So dt and sum, this is this concept. Then I sum the energy, okay, the heights. And then I need to divide it by the time I decided I'm going to sum t, so I'm going to divide by all the time. So this concept is actually doing average for a continuous thing. And the way to write it is actually take the function and do this sign of average t. It means that you're going to do a continuous averaging. So that's what I did here. And now the units are okay, because when I'm going to multiply this by this, the second going to go, when I'm going to multiply by the area, the meters are going to go, and they're going to stay only with joules. Okay? So let's actually do it. Okay, so by t. So A, it's a given thing, okay? And if I'm gonna try to solve this integral, you see that I can take all of these guys outside. So this is E squared 0, C mu 2. And the only thing that I left with is sinus square inside the integral. And I'm gonna give you the answer immediately. The answer is half. This integral, it's not that important for the physics, it's for math, but that's the idea here. Perfect. Okay, we did this one. And this was the second, hardcore question about EMR. So now I want to move on to the next question, which is going to be really similar, okay? We're going to do small changes, but the concept is pretty much the same. I just gonna a little bit give you complication, because right now you understand the basics idea, and now on you can move on to a more general stuff. So this is the idea. So you can think about it. The question is that the nurse come by, okay, la 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 la, I'm the nurse, I'm coming by, and I see this X-ray gun, and I give it a little, you know, like elbow, okay, and right now it's moved to somewhere else, okay, the beam pointing in another direction, a random direction, okay, so let's see what's happened, okay, and it's gonna be a great summary, okay, so this is the second question, so I'm gonna leave this one here, so the nurse hit the beam, they hit the gun, and the beam changed direction. So magnitude stayed the same, but now on it's right now we declare a new time. Okay, this is right now time 0 since she hit with the elbow of the gun. So these signs become right now cosines. Okay, and this is alpha multiplied by 2x plus y. What's going on here? Okay, we're gonna talk about it, don't worry, it's important, that's the reason we're doing it. We'll make a t, okay, and in which direction? Holy crap, okay, she got a good elbow, okay, that's what I can tell you. It's 2y squared. So what's happened to the electric field? So right now the electric field is not pointing in the x direction, the original x direction. Right now it's pointing in some x direction and 2 times more in the y direction, minus y direction, okay? So it's kind of what I drew up here, okay? It's still pointing at the x direction, but it's pointing more hardly at the y direction. So the direction is actually kind of this thing, okay? So perfect. And now let's move on. So the question to you is, what is the wave vector? Okay, what is the wave vector? The wave vector. Promise I will tell you about it, right? Wave vector, k. Okay, what is, let's do, as a vector. What is equal to, okay? So the wave vector is actually the direction that I'm pointing in this one. This is the direction. If I want to find only the direction, is where this thing is moving to, okay? So the direction, okay? The direction where it's moving to, okay, so I'm gonna take this term, and remember that this was at the beginning k multiplied by x, but right now it's general. I know it's k multiplied by r, dot r, okay, it's a vector, this where I am in space, okay, r is x, y, and z, sorry, let's not do cursive here, and k is actually a vector, kx, ky, kz. That's what's going on here, okay? And also, if you remember for the previous time, here it was not a plus, it was a minus, okay? So in order to solve the equation, I need first of all to understand that this one needs to be changed to a minus. Why a minus sign? Because otherwise this is not k, this is minus k, okay? So this is not correct right now, this term. It's not exactly k dot r, it's minus, but I can use special property of cosines, which is cosines of minus something is actually equal to cosinus the same thing. Why so? Cosines have a really special thing that when you look at the mirror, you see the same image, okay? If this is the x-axis, the y-axis, and this is kind of theta, okay? So cosines is actually going from here to here, but from here to here. So you can think about this thing as a mirror. Somebody is looking, hey there, hey you there. Okay, so it's look the same. So I can also take this one and this one and say they're gonna, this one and this one, they're gonna have the same value. So I can actually add a minus and nothing gonna change, no harm being done. So it's actually E0 cosines minus alpha 2x plus y minus omega t. Now it's correct. Okay, now I can say this thing here is actually k vector, okay, dot r vector. Now it's correct. And if I look at my r vector, it's actually 2 at x, 1 at y, at 0 at z. That's what's going on here. What's going on over there? So at alpha, so I can see, it's 2 alpha, sorry, this alpha is a sorry, okay, never mind. Okay, so sorry about that. I was a little bit confused. This is x, and k is actually what? It's minus 2 alpha, right? Because x and y belong to r, as I mentioned before. Okay, minus 2 alpha, and minus 2 alpha and minus alpha and 0. That's what I have here, k. Okay, let's do it more even clearer. Okay, sorry about that. So minus alpha, minus 2 alpha, minus alpha, 0. That's what you have here. And this is multiplied by x, y, and z. Now it's correct. And now I found my vector k. I found it, okay? What is the direction of the vector k? Okay, the direction of the vector k can be easily found, okay? I just need to take the vector k, let's clean this part, k, and divide it by its magnitude, right? So k direction, the direction of k is equal to, direction k is equal to, and this is the magnitude k, sorry, k itself, divided by k the magnitude, right? Take the vector, take out the magnitude, you left only with the unit where I'm pointing it. So this one at the top is, can take minus alpha outside, it's 2, 1, 0, divided by the size, so I square this thing for alpha square plus alpha square, right? That's what I get. I can get rid of the alpha, right? So the direction is actually k pointing at minus 1, 5, 2, 1, 0, okay? So some of you maybe thought that, hey, here's the direction. Not exactly, okay? This one is actually pumped, okay? Because it's not a unit. You can see 1 is big, it's already 1. Now you're gonna do something with 2. Okay, so you can actually get, and you can normalize this one part and find out what is the direction, but also in this way. And also, I want to ask you, this is the magnitude, right? The magnitude is actually alpha 5, right? This is the magnitude of the vector, right? So I can ask you, what is the wavelength of the X-ray? Huh? Now you can find it using alpha, if alpha is given. So we know that k is equal to 2 pi over lambda. So I can switch them apart. Lambda is 2 pi over k, and it's equal to 2 pi over alpha square root of 5. So I can find what is the lambda, how the wave look like. So what is the distance, okay, that I finish the period, okay? So I can find this term. And the next thing I want to do is found B. Okay, let's found B. And right now we said, okay, it's perpendicular to each other. I remember this one from the previous, but right now I'm pointing in really weird direction, right? So let's come up with the method, okay, to solve it. So a way to solve it, if you have a crooked electric field direction, you can use the math, right? If they are perpendicular to each other, B vector is actually 1 over C, right, to correct this term, right? At K direction, cross E, right? So if I'm gonna do the cross, always when you do a cross, this is X, Y, you're gonna get the perpendicular result to both of them, okay? Also, in a general case like this. So that's all I need to do, okay? So if I do the cross, so let's do it. Oh, why I did? Oh, never mind. Let's write from the beginning. B 1 over C, K hat, E vector equal to. This is really important. Let's give it a star. Okay. So this one is 1 over C minus 1 over 5, 2, 1, 0, right? And now I have, this is what? K hat, right? Cross E, okay? So this is E0, and this is E0. E0 cosines, actually it's this term, okay? This is this term. All of this going here. Perfect. So when I do it, I'm taking all the constant outside, it's a minus, and it's become positive because of the cross, because this and this. Cosines, the same thing, c square 5, determinate x, y, and z. 2, 1, 0, 1 minus 2, 0. And this one is equal to, this one is equal to E0 square root of 5 cosines, same thing over c, and the z direction, which is no surprise. Why? Because E, okay, the electric field is moving at x and y, okay? So the x and y perpendicular thing must be at the z direction, right? That's what's going on. If it's still locked inside the xy plane, so the propagation b must be perpendicular to it, okay? Not the propagation, sorry, the magnitude changing should be, and so you see what that's what happens. So this is a flat line, x and y. So in the beginning it was pointing in this direction, okay? And now it's pointing in this direction. But if you want it to be perpendicular, it's be this perpendicular to this one, and it's also perpendicular to this one. So it still stay in z. So this make sense, okay? So we finished the class, okay? I know it was a hard class, a lot of math, but it was important to talk about that. And this subject is so huge. It's a different class, but we must have to talk about it, about how, you know, the magnetic field that we learned in the end of the class and the electric field was also in the class, join up together to be something incredible, light, okay? Guys, I really enjoy giving you this class and this lecture. If you enjoyed the video too, I would like you to like the video, subscribe to the channel, support, and if you have any question to ask me, something that was not clear, comment below. You can add the time, okay? Add the time, the specific time it's happened to you, and then it's gonna be easier to me to click on it and jump in the middle of the video to do exactly the point you did not understand and grasp the idea and explain it to you. Also possible. And next week we want to talk about a really special subject. It's about light, that the method that we actually understand that light is a wave. It was not that clear, okay? For you it's clear because you hear it since you are a child, okay? But at the beginning it was a really hard question to ask. How light behave, okay? The thing that, you know, the basic thing that give light, okay? So that's what we're gonna talk next week. So stay tuned. Gonna see you next week in the next video of our channel, and subscribe, like, comment below. Appreciate it. Love you all. Enjoy teaching you. See you next week. Goodbye.